Hello everyone. It's my pleasure to share our work TQNet Mixed Contrastive Representation Learning for Heterogeneous Text Question here. I'm He Zhu, come from the University of Chinese Academic of Science. First, I would like to introduce the background of our work. Nowadays, more and more users prefer to learn courses or take text questions from the online learning system. Behind the online system, the automatic model is the most important module to provide a personalized test and practice list to effectively improve the weak knowledge of different users. However, it could be hard for the automatic model to understand the test question, which results from first, heterogeneous test question. The test question may contain of text, formula, and images as shown in Figure 1, which needs a well-designed network to process different model data. And second, the labeling cost, because each test question needs professionals to provide correct and detailed answer, which costs much more expensive than traditional AI labeling task, and is usually difficult to build a general dataset. Previous solutions are mainly based on two approaches. One approach is to design the heterogeneous model and train the model on the supervised dataset, but the dataset could be small because it's expensive to collect and build the questions and answers. And another approach is modeling the test question as pure text input, which ignores the visual content and uses the method of the natural language processing to deal with the question data. Both of the above solutions have their limitations. Thus, in this work, we propose the TQNet to effectively extract the representation of test question and design an unsupervised heterogeneous representation learning framework. Moreover, we propose a supervised method to improve the educational downstream tasks such as the similar test question and knowledge point classification. Here, I would like to introduce our training pipeline and model architecture. The training pipeline has 3 steps. In step 1 and step 2, the network will employ an unsupervised way to learn the representation of test question. Step 3 is for the downstream task with supervised data. As shown in Figure 3, the TQNet consists of the ResNet as a visual encoder and the BERT as a text encoder, and the multi-height attention module as a fusion model to fuse different model features. In the first step, the text encoder of TQNet will use the mask language model as a pre-test task to train on the question dataset. As a traditional mask language model task, the text input token will be masked with 15%, in which 80% changed to mask token, 10% to not modify, and 10% changed to other words. The encoder needs to predict the ground truth input token. And in step 2, we will use contrastive learning to learn the heterogeneous representations. Contrastive learning is to attract positive pairs and repulse negative pairs. The positive pairs here consist of 2 argumentation wheels of the same test question, and the negative pair are from the 2 different questions. The augmentation of images contains crop, resize, flip, and color jitter. The augmentation of text contains the random mask and the dropout. Notice that our proposed method uses heterogeneous representations to do the contrast. To compare, previous multi-model contrastive learning methods were used to attract different model features in the same latent space, which is unsuitable for model incomplete test question data. Moreover, step 3 is for a supervised downstream task. If we have the label of question data such as a similar question or knowledge point labels, we could choose the positive pairs in a supervised way as shown in Figure 4 and 5. In this training process, would greatly help the network to understand the relationship between different test questions. Next, we will introduce an experiment section. First, I would like to introduce a pre-trained dataset, which is an unsupervised dataset consisting of nearly 86,000 truth questions, 42,000 blank filling questions, and 49,000 calculation questions. In this test dataset, around 13% of questions have images, and the maximum number of images in one question is 10. Second, the downstream task dataset contains two tasks. One is a similar test question task, in which the model needs to predict whether 2 given questions are similar. And another is a knowledge point prediction, which is a classification task. The similar test question dataset have 27,000 trained question pairs and 45 test question pairs. The label is a binary representing whether the given pair is relevant or not. Specifically, each question in the train and test dataset will have at least 5 similar questions, and there is no overlap between the train and the test datasets. In default, 2 random questions are not similar with a high probability. Here we use precision at 5 as a metric to evaluate the performance of this task, which represents the average precision of similar prediction. Knowledge point prediction has 100,000 streamed questions and nearly 30,000 test questions. Its labels has 391 categories. After pre-training, we test our proposals on these two downstream tasks, and shown in Table 2 and 3, our proposal greatly improved the downstream performance compared to previous method. To better understand the performance improvement, we designed ablation studies as shown in Table 4. The results of the different pre-training settings shows that MLM of Step 1 and mixed contrastive learning of Step 2 both effectively improve the downstream performance. The results of the different fine-tuning settings also verify that our proposed supervised contrastive learning is beneficial for the downstream task. Then, we test different model fusion methods, which we divided into two methods. One is a joint fusion, which uses different tokenizer and share the same encoder to fuse the multimodal inputs. Another is coordinate fusion, which employs two-stream encoder to process different modal input and fuse the features in the latent space. As shown in Table 5, the result shows that the coordinate method has better downstream performance. Thus, our TQ-Night uses the coordinate structure. Moreover, we want to figure out the advantages of our multimodal TQ-Night compared to the previous single-model network. Here, we split the similar test question dataset into three match types. First, text-to-text. The two questions of the pair are both pure text input. Second, text-to-image. One of the question pairs in the pair contains image input and another is a pure text input. Third, image-to-image. Both two questions contain image input. The results as shown in Table 6, indicating that our multimodal contrastive learning helps to learn better representation of questions. Thus, we proposed that the visual contents were necessary, which greatly benefits the representation learning. In this paper, we improved the pre-training method of the previous text-only text representation with a two-stage contrastive learning method. We also explored the fusion method of the image content, where a model named TQ-Net and mixed contrastive learning was proposed to process the heterogeneous data. Moreover, we provide unsupervised and supervised training method, which helps the model to effectively learning the multimodal representation of question data. That's all. Thank you for listening.